Hi there, my name is Max Herson, and I'm a PhD candidate at Simon Fraser University, and I'm here to talk to you about the amplification of plunging flows in bedrock canyons. And a wise person once told me that when you're looking at data from a river, it's important to contextualize that data with how the river actually looks. And so I'll be taking every opportunity here to show you imagery of the river that I'm studying. And finally, you might see me jumping around a little bit from slide to slide as I try to find real estate for my video. Whoa, just like that. To start with a little bit of background here, bedrock rivers control the rate of landscape evolution, and that's because they act as hard points in the landscape that are slower to erode or respond to climate or tectonic signals than their alluvial counterparts. So as the landscape is trying to develop, or the graded stream profiles are trying to develop, that development gets hung up in these bedrock sections. And we know that sediment transport is a major influencer of bedrock erosion. And that's best described by the tools and cover concept. You can imagine particles bouncing along the bed, and every time they hit the bed, a little bit of material can be removed. But these particles can also pile up and protect the bed from any kind of erosion, if it's abrasion or other types. And so you can imagine that at very low transport stages, assuming a steady sediment supply, that the bed can get fully covered and protected from vertical incision. At moderate transport stages, all of the bed material will be mobilized and you'll have maximal incision. And then at very high transport stages, these hop lengths get longer and longer, and some of these particles end up in the suspension regime, and your erosional efficiency actually goes down. And so we know that moderate transport stages are the most effective at bedrock incision. And obviously, sediment transport is driven by hydraulics. And so in this way, bedrock river hydraulics link climate and tectonics through landscape evolution. I'm shrinking. So when you're talking about actively incising bedrock rivers, canyons naturally come up. So what do the hydraulics of bedrock canyons actually look like? Well, for a nice straight segment of river like this, you might expect the maximum velocity to stay on the surface in the center of the channel. But in 2014, Vendetti et al. Actually showed that the maximum velocity tends to plunge down and towards the bed in these sections of canyon. And that's because of two large counter-rotating secondary circulation cells that drive downwelling, shown in blue in the center of the channel, and upwelling along the channel margins, shown in red. And these plunging flows have been observed in canyons that have very small width to depth ratios, so they're quite steep walled and quite deep. As well, these walls tend to undulate, and so you end up with big wide sections of river that can quickly be constricted. And when we see these constrictions, we oftentimes associate those with deep scour pools below them and a subsequent widening. And this has been coined a constriction pool widening sequence, and that's been associated with plunging flows. However, plunging flows have only ever been observed at low flows, and we know, or in flumes, and we know that at low flows the bed is likely fully alluvial, and bedrock incision is unlikely. And so my research objectives here are to investigate the flow in bedrock canyons at higher discharges. So I want to look at both moderate and low discharges. And I want to do this in order to determine if plunging flows exist at higher discharges, to assess how plunging flows affect alluvial cover in the channel, and to reflect on how these plunging flows affect the morphologic evolution of bedrock rivers at the reach scale. And so our study site is a canyon of the Fraser River in British Columbia, Canada. And it's 2 kilometers downstream from the previous observations of plunging flows. It's called Alexandra Canyon, and this reach has a mean annual flow of 2,700 cubic meters per second, a minimum flood of 5,500 cubic meters per second, meaning that's the minimum flood that you're going to see in any given year, and a 2-year flood of 8,420 cubic meters per second. And I'd like to show you a little bit of drone footage here in order to just contextualize this data. Here you can see the constriction of the initial canyon confinement. You'll see that there's upwelling in the channel margins with a small widening in this section of the river. Just to give you a sense of scale, this boat is 23 feet long, or 7 meters long, so it's quite a large river. And then at the distal end of the canyon, you see quite a substantial widening. And that original constriction and final widening are about 50%, so the channel becomes half its original width, and then at the end of the canyon, it doubles in width. And this is considered a sort of prototypical constriction pool widening sequence. And so we decided to collect some data in this reach. We collected velocity data using acoustic Doppler current profilers in both centerline transects straight down the middle of the channel, as well as zigzag surveys. We also collected bathymetric data using multi-beam echo sounders. And here are the boats set up with that equipment. And you can see that we actually have two ADCPs running off of either end of the boat, or either side of the boat. We collected one set of observations in June at 5,500 cubic meters per second, which is close to the peak flow of that year and representative of the minimum annual peak flow. We also collected a low flow observation in August on the falling limb of the hydrograph at 2,175 cubic meters per second. And here's what that data looks like. We've got zigzag surveys and transects over top of the multi-beam derived bathymetry. And in order to smooth over turbulent scales in this data, transect surveys were treated with a ensemble-wise average of 11 points, and zigzag surveys were treated with a spatial average of 5 meters. And then we render this data into interpolating software. And so here are some of the results. At moderate flow, the bathymetry shows a very deep scour hole right in the narrowest section of the canyon. And interestingly, you see sediment waves upstream and downstream, but not in that deepest part of the canyon. At low flow, we see a substantial filling in of that pool. And at this point, we also see sediment waves all the way through the canyon. And if we difference these two observations, we notice that there's quite a large volume of sediment that's been deposited in that 3-month period. This sediment patch has an average depth of about 4 meters and a maximum depth in the deepest part of the pool of 14 meters. And it's interesting to note that both upstream and downstream of that sediment patch, the bathymetry does not change so substantially. And so we also observed a plunging flow here. So I'm showing a ship track in this panel with the associated velocity profile of the current observation in this panel. And so right now the ship would be there. And then up here we've got that same data, and it's just graphed out where we've got distance from the canyon entrance on the x-axis, depth on the y-axis, and then the color refers to the velocity magnitude. And this black bar here represents this current still frame. And so here you can see the boat's right there, and we've got a regular velocity profile. As we move towards the canyon entrance, you can see that we are now right where the canyon constriction is, and this velocity profile starts to flatten out quite a bit. From there, we can see that in the pool, the plunging flow has fully formed. The boat is right there in the pool, and you can see that our velocity profile has bellied out at the lower end. And then downstream, a regular velocity profile forms once again. And here's what that data looks like if you just watch, the evolution of that velocity profile. And I tried really hard to get this black line and this video to line up, but if you let them play for long enough, they go out of sync. And so if you take a bunch of those observations and stack them, you can start to see trends in the flow. And so at low discharge, we've got a series of these transects stacked, and then also at moderate discharge on the bottom here. And the first thing I'd like to point out is that transect 1 and 2, as well as transect 3 and 4, are collected on either side of the boat with separate instruments, but simultaneously. And they show very good agreement, which is promising for the quality of data. Sort of looking at the differences between the plunging flows here, you can see that at moderate discharge, the plunging flow is elongated and strikes the bed further downstream than at low discharge. That momentum is better maintained through the canyon and through the deepest part of the pool. And that it sort of fits the geometry of the canyon better. You can see that at low flow, it sort of spills into the start of the canyon without taking up the full volume of that pool, while at moderate flow, it fills that full pool. And so graphing out some of this data, we can take another look at it. And so here we've got velocity in meters per second on the left axis, and the proportional height of the maximum velocity in the water column on the left axis, with 1 being the maximum velocities on the surface and 0 being the maximum velocities on the bed. And on the x-axis here, we've got distance from the canyon entrance. And so what you'd expect to see is a green surface velocity being higher than a blue moderate or depth average velocity, and that is then higher than the red near bed velocity. And the maximum velocity is seen close to 1, meaning that it's on the surface. And when you display the data in this way, the plunging flow becomes quite apparent as the green and red lines invert, and the black line is driven towards the bed. And so a couple things that you notice right away is that at low discharge here, the mean velocity drops off substantially as it enters the canyon, while at moderate discharge, that mean velocity is maintained much further through the canyon, and when it does drop off, it's dropping off a lot less. Another thing that becomes apparent is that the moderate discharge observation has the plunging flow already started when it comes into our survey. The velocity, the maximum velocity is about halfway down in the water column as it enters our survey here. And then the final thing you'll note is that the point at which the plunging flow hits the bed is about 200 meters at low flow, but at moderate discharge it hits the bed at around 300 to 350 meters. And finally, I'll just say that none of these flows are transcritical. The highest observed Froude number that we saw was about 0.4. And so here's what that data looks like in 3 dimensions. You can see at moderate discharge, the plunging flow coming into the canyon, going down into the water column and striking both of the walls before it dissipates. At low discharge, we see a very similar effect. However, the velocity magnitudes are much lower, and the dissipation just happens a little bit earlier. The vertical component of the velocity also shows that secondary circulation, those 2 counter-rotating secondary circulation cells, where you can see downwelling in the center of the canyon and upwelling along the canyon margins. And again, at low discharge, we see a similar effect, but the velocity magnitudes are much larger at moderate discharge. And so what are the implications for channel morphology? Well, moderate discharge plunging flows fit the canyon morphology better, and that's to say that they occupy the full length of the pool in the canyon, while the low discharge plunging flow seems to spill into the early part of the pool before petering out. The sediment component of pool morphology adjusts to plunging flow hydraulics. So that's to say that as the plunging flow is elongated and becomes stronger, so too does the pool become elongated and deeper. And we believe we're seeing a full sediment mobilization in the deepest part of the canyon at moderate discharge. And this is evidence that there's an annual sedimentation cycle happening here, where at low discharges, these canyons are filled in with sediment, and then at the peak discharges each year, that sediment is blown out. And so some of the implications for bedrock erosion here, if we tie this back into the theory, are that we expect widening at low discharges when the bed is fully protected by an alluvial layer, and only particle deflections into the walls are possible. We expect incision at moderate discharges when we're seeing full sediment mobilization in the deepest part of the canyon. And, we don't have any observations at higher discharges, but we believe that the bed likely remains exposed. And as those near bed velocities continue to rise, that incisional efficiency for the sediment inputs decreases. And this is some evidence that moderate discharges act as a morphogenic flow and are responsible for shaping the bedrock component of the canyon morphology. And so to wrap up with some conclusions here, plunging flows are amplified with discharge. Moderate discharge plunging flows fit the canyon morphology better. And these plunging flows are driving an annual sediment cycle. These plunging flow hydraulics are obviously relevant for bedrock incision, as we believe we're seeing an incisional flow at moderate discharge when we're seeing quite a strong plunging flow. And we believe that this is some evidence to suggest that moderate discharges may be the most impactful morphogenic flows. And this would agree with alluvial river observations, where we see that a 1 to 2 year flood is the most impactful in controlling the morphology of a channel. So thank you for the opportunity to share. I'd like to thank my lab group for their insights on this work. I'd like to thank everybody that was involved in data collection, and I'd like to especially thank my partner and temporary office mate, as a lot of this work was done from home during the pandemic.